Section 6.3, Solving Systems Using Elimination. I can solve systems by adding or subtracting to eliminate a variable. Big ideas here. Systems of equations can be solved in more than one way. Some equations are written in a way that makes eliminating a variable a good method to use. Example 3 here, if we look, it doesn't look real easy to eliminate, and we don't have opposites like yesterday. So what we have to do is we have to get opposites. If I look, negative 2 and 7, I can't multiply negative 2 by a whole number to get to 7, and I can't multiply 7 to get to 2. But if we look at 15 and negative 5, I can multiply here. If I multiply the 5 by 3, I get negative 15, and 15 gives me opposites. So instead of yesterday where we multiplied everything by a negative, today we're going to multiply by whatever we need in order to get opposites. So I'm going to multiply the entire bottom equation by 3. And remember, we have to do it to every piece in order to keep it equivalent. So I'm going to have 21x minus 15y equals 51. And take a second just to make sure that you multiplied to every piece and that your signs are the way that they should be. Plus, minus, plus here. Now I'm going to bring down my first equation just so I can see them together a little bit easier. And now that I have opposites, I can go ahead and add. Here, 21 plus negative 2 gives me 19x. Negative 15 plus 15y gives me 0 equals, and I have 19 here as well, 51 plus negative 32. I can divide to get my x by itself, and x is going to be 1. Now that I know what x is, I can plug it into any equation that has both an x and a y. So I can plug it in here, 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 doesn't matter. I like to do it to one of my original equations because I know those are right, and I haven't changed them, so I'm still dealing with the original values. I haven't made them bigger or anything, so my numbers are going to be a little bit easier to work with, usually. Plug it in for x, everything else stays the exact same. Multiply to get negative 2. And bring everything else down. Add 2 to get my y term by itself. And divide. And y is going to be negative 2. So my ordered pair again is still x and y. If we plug these in, it makes both equations true, so we know that our answer is correct. Feel free to pause here and give this a try. Now, what is the solution of the system using elimination? Again, if we look here, I have negative 5 and 3. I can't multiply those to get to the same value. But here, negative 2 and 6, if I multiply by 3, I get to negative 6. Compare that with 6, and we have opposites. So I'm going to multiply so that my y gets to negative 6, which means the top one by 3. And I do that all the way through. Negative 15x minus 6y equals 18. I'm going to bring down my other equation as well. And again, real quick double check, I changed the top one, all of them are different, my signs are the way they should be, and I dropped down my second equation exactly right. Now that I have opposites, I can go ahead and add. Negative 6 plus 6 is how I get to 0, so that's gone. Here I have negative 12x equals 24. I can divide to get rid of my multiplication, and x is going to be negative 2. Now that I know what x is, I can plug it into any equation to find y. Substitute it in for x, and everything else stays exactly as it's written. Multiply. We add to get rid of the minus 6. And then divide to get the y by itself. So my ordered pair is negative 2, 2. Example 4 here, solving a system by multiplying. If we look here, I have a 3 and a 4 for my x's, and a 2 and a 3 for my y's. I can't get from 3 to 4 or 4 to 3 by multiplying by an integer, and I can't get from 2 to 3 or 3 to 2 by multiplying by an integer. So what we're going to have to do here, guys, is we are going to have to change them both. I can multiply 3 by 4 to get to 12, and I can multiply 4 by negative 3 to get to negative 12. I also could have chosen to get opposites with my y's. Between 2 and 3, the smallest number they both go into is 6. So I can multiply by 3 and multiply 1 by a negative 2, and that gives me 6 and negative 6. I could have changed my signs and done like a negative 4 and a positive 3, a negative 3 and a positive 2 as well. And we don't have to use the smallest one. That just keeps our numbers that we're using smaller and easier to work with. So it does not matter here if you do x's or y's. I'm going to go ahead and do the x's. So to get my x's to be opposite, again, I'm trying to get one to be 12 and one to be negative 12. So I multiply the top by 4 and the bottom by negative 3. And whatever I do to one piece of an equation, I have to do to all of them. In my top equation, I have 12x plus 8y equals 4. And in the bottom, I have negative 12x minus 9y equals 6. Combine our equations. Now we can add 0, negative 1y equals 10. Divide by the negative 1, and we get y equals negative 10. Now that I know y, I can substitute it back into any equation to find x. 3x plus 2 times negative 10 equals 1. Multiply first and then bring down the rest of your equation. I'm going to add 20 to get rid of my subtraction, and divide by 3 to solve for x. So I get x is 7. 7, negative 10. Now, if we'd have eliminated our y's, we would have gotten to the same place. We just would have found our x value first and had to substitute it back in to find our y. But it would have worked in the same process. Same idea here. If we look, you can go ahead and pause and try this if you'd like. We're finding the solution using elimination. So 4 and 3, I can't multiply one to get to the other. And 3 and negative 2, I can't multiply one to get to the other. So I'm going to have to change both. And the one that I'm going to pick here are my y's, because I already have a different sign. So I already am going to have opposites. Now I just need to get the same values. I can get to 6 by multiplying 3 by 2 and 2 by 3. 6 and negative 6. Again, we could have done 3 and negative 4 or 4 and negative 3 here to get the y or the x's as well. But if I don't have to multiply by a negative and remember to change signs, it's going to make things just a little bit easier. So 2 on top to get rid of my y's, and 3 on bottom to get rid of my y's. Multiply all the way through. 8x plus 6y equals negative 38. 9x minus 6y equals negative 30. And again, double check. Did every number change? Yep. Are my signs right? Plus, plus, minus, and plus, minus, minus. Perfect. We can add these up because we have opposites. And we get 17x equals negative 68. Divide by 17. We get negative 4. Now that we know x is negative 4, we can substitute it in to one of our equations. Again, it doesn't matter which one. I have 4x is negative 4, so I substitute that in. Plus 3y equals negative 19. Multiply negative 16 plus 3y equals negative 19. Add 16 to move it to the other side. I have 3y left on the left and negative 3 on the right. To get rid of the multiplication by 3, we're going to divide by 3. And y equals negative 1. That makes my ordered pair always x, remember, first, and then y. So x, y, negative 4, negative 1. Example 5 is finding the number of solutions. In the last few examples, we got down to ordered pairs like negative 4, negative 1, 5, 7. Things like that are always going to be one solution, and those occur whenever we still have a variable left. Anytime that our variable completely disappears, however, it's either going to be no solution or infinitely many solutions. So if we look here, we don't have opposites, but we can get some. If I multiply the bottom equation by -2 all the way through, I'm going to have -2x minus 6y equals -18. I can bring down this top equation as well. I'm just going to rewrite it so it's a little bit more organized. And now that I have opposites, I can add these together. -2 plus 2 gives me 0. -6 plus 6 gives me 0. So on the left side, I have 0. On the right side, I take -18 plus 18, which is also 0. That's true. Anytime we get a true statement after our variables are gone, it's going to be infinitely many solutions. And that means, like as far as a graph were to go, it would be the exact same line and the same graph. This is the same thing we did with substitution, but in substitution we got things like 14 equals 14, for example. Now, how many solutions does the system have? Feel free to pause here and give this a try if you'd like. If we look here, we don't have opposites. We have the exact same on each side, so we need to get on top and bottom. So we need to get opposites. In order to do that, I'm going to multiply one of them by -1. It doesn't matter if we do it to the top or the bottom. That part doesn't matter as long as we change one of them. And remember, we multiply that all the way through, even to the other side of the equal sign, the entire equation. -1 times -2 gives me positive 2x. -1 times positive 5 gives me minus 5y. And -1 times 12 gives me -12. I'm still going to bring down the equation that I didn't change, just to make it a little bit more organized and keep it all together. Now, I have opposites, so I can add them up. 2 plus -2 is 0. -5 plus 5 is 0. So on my left side, I have 0. On my right side, -12 plus 7 is -5. And here, 0 does not equal -5, so we have no solution. Either one of those, this or this, would work as far as your answer goes. Some of you, when you solved this, might have had a positive 5 there, and that would have been because you multiplied by a negative in the other equation, and that's fine. It still gets us to that no solution. And again, we only ever get no solution or infinitely many solutions when our variables completely cancel out and are gone. Real quick recap here for section 6.3. Systems of equations can be solved in more than one way. We've done graphing, we've done substitution, and we've done elimination. Some equations are written in a way that makes eliminating a variable a good method to use. Anytime we have a system where substitution isn't very easy and we'd have to use fractions, it's easier to use elimination and just multiply both to get them to be eliminated than it is to try and distribute fractions and combine like terms with fractions. And that's all I have for section 6.3.